Good morning, everybody. I hope you had a good evening, and we continue with the second day. And well, we look at line planning, a little bit of timetabling today, how we do that in practice. And this is then followed by Anita's approach, how you do that with mathematical methods. I want to start with the same slide which I used yesterday. And here I showed you the design process, and I mentioned the three approaches: manual planning, computer-aided planning, and mathematical optimization. And I'm not going to do manual planning because this is difficult to show. Manual planning means we do most of it manually, maybe using some Excel sheet or whatever. I want to show you computer-aided planning. And by that, I mean that we use a computer screen, a computer program to input the data, especially the line plan and the timetable. So this is why you see here a computer and a human being. So the human being is creative, has experience, and tries to develop a good solution. Then we have the second part, determination of impacts. So that would give us, for example, travel time and operating costs. This is something which is done by the computer. And then we look at the results and we analyze the results. So we look at the computer results. It's no direct feedback because you first try to identify deficiencies and then you go back and you modify it. So the idea is the planner is the creative person, and the planner is supported by a computer model. And yeah, this is the process I want to show you. To a certain extent, you can use optimization, mathematical optimization in this process because we have mathematical models there, like the traffic assignment model I showed you yesterday. Now, to make it a little bit more practical, I want to start not with slides. I want to start with a little demo. And this is pretty close to what we will do in the second part this morning. We will look exactly at this network, and I want you to suggest solutions for that network. Since you don't have the software, I will show you later on a way how you can provide us with solutions, and we will run the solutions for you. Now here, I'm assuming I'm a planner. I have this simple network, but let's assume it was a real network. And well, in gray, I already prepared some data which provides me with a result from my travel demand model. The wider the bar, the gray bar, the more travelers we would expect. So this is just assuming people travel by taxi, and the bigger the bar. So I get already some idea that I probably don't need a line route somewhere here at the edges, but I have something around this city center and maybe up here. So with that and with my local knowledge, I would now start creating lines. And I really start from scratch. So I create a new line in my computer-aided process. And well, I need to select certain, the transport system, it's bus and a vehicle combination and an operator. And then my line has a name, but now I start with the first line route. So line number 1, the first line route in the first direction. And then I start, and now it's absolutely trial and error. There's no rule how I do it. It's only my experience. And I work like a greedy algorithm, and I look at the quick gains, and I start with a line route, for example, this one. Yeah, that's my first guess. I want to check if that works. And I accept that line route, and here it is. Now it's only a line route. Now I'm going to add the timetable. So you see, it's I need to do work. It would be nicer if a computer could do that for me. Now I create vehicle journeys. So I have an empty timetable here, and I want to say, okay, I'll start at 6 o'clock in the morning, and I want to have some type of regular service. So until, let's say, 8 o'clock in the evening, I want to run every 20 minutes. And you see, here I have my timetable. And yeah, this is what the timetable looks like. Now, I go back to my line route. You already see here, it now has 43 service runs. And to make it simple, I'm just create the opposite direction by just copying it, including the vehicle journeys. So now I created my first line. I can look at the timetable, and you now see, maybe I'll zoom it out a little bit. You see that we have a timetable in 2 directions now. And now I prepared a procedure. We don't need to understand all of that procedure, but in the end, it's pretty simple. What we do a public transport assignment, what I showed you yesterday. And I also, here I apply an algorithm. I do line blocking, vehicle scheduling. And then I have a method which computes the cost. So there are cost values for every line and for every vehicle. They are embedded, I can show you, for the vehicles. I have cost rates, I hope. So I have the capacity here, and I have cost rates. And now I just run this procedure. And the next thing I do, I look at the results. And here, what you see the volumes. That is the Q is the volumes. R stands for the number of runs. So we have 3 runs per hour. We have this 20-minute headway. And X stands for the saturation. And now I already see, okay, my service frequency is not good enough. I have here I'm oversaturated. Maybe a little bit larger, you see it better. So here you see I'm oversaturated. So I either need to create an additional line, or I need to increase the service frequency. So this is one first result. I also get information which I compiled together. We have the nodes in the network and so on. But here you see I have the service kilometers, I have the service time, I have the number of vehicles I need to buy, I have the operating costs, and I see at the moment for those passengers which are transported, they need 27 minutes and there's no transfer. Well, if you look at the network, you cannot do a transfer. Either you stay at home, people are not walking in this system, or there's no possibility to transfer because there's only one line. Well, and then I would continue with the next line and the next line and so on. And I would always observe my values, how they change. And you see, the biggest disadvantage here is that once I created a line, oh, it's like you wrote one page of text. You don't want to delete it, even if it's maybe not so good. After some time, you notice it. So it's manual work, and this is why we are looking for methods making that easier for us, providing us with solutions that are not man-made but supported by a algorithm. So that is a first idea to show you what I mean by talking about computer-aided planning. Now, yesterday I showed you those questions. The planning task, what kind of system is appropriate, and so on. I added for today 2 additional tasks. They are not really related to the actual planning, but it's part of the planning process that you first define the scope of the planning task, and then you get everything ready you need, and I call that determine your planning parameters. Then we talk about the appropriate system, and we will go step by step through all the steps of a planning task. I'll start with the scope of the planning task. We already talked about that yesterday. We need to define what is our task, what is the scope. And here you see a maybe typical situation. You have railway, you have regional buses, you have local buses. You may have the same system inside a city where you have metro system, where you have buses, more important buses, connecting places, and you have feeder buses. Now, the first thing is to understand what is your responsibility. If you do bus planning, often the railway is there. They provide you with with all the background information. They are to a certain extent a constraint for you because they decide on the timetable, the arrival and departure times of the trains at those locations. So get that clear first. A second part of that is, it's not the case that we always plan for an entire city. Some cities, I've seen it over the last 20, 30 years, they sometimes they delete their entire bus network and they start from scratch. Munich has done that something like 10, 15 years ago, for example. So you really start with a new bus concept. But often you just amend an existing system. Here's an example of a planning we did for the Stuttgart region. You see here in the middle the Stuttgart city, and you see the rail network. And since it's hard to extend the rail network, it would take some time. they thought that they would install express buses. And here the task was, out of a number of express buses, to select 2 or 3 or 4 of them which were most feasible. So here the planning process focused on amending lines. And here the question was, are they in, well, they shouldn't compete with the S-Bahn lines. They should provide additional direct connections. Second task, define your planning parameters. What do I mean by that? We yesterday looked at a travel demand model. So you need, however you do it, with a model, without a model, you need information on the travel demand. Maybe from counts, but more ideally using a model. And you need to determine the given supply. For example, the train network. And then you need to collect information on the vehicle characteristics. So for example, the capacity of the vehicles and all the vehicles you have available. And you need to determine the cost rates. So this is what I mean with determining the planning parameters. Then, next step, often this is already decided and it's not the scope of your planning, but sometimes the question is, shall we have a bus or shall we have a rail-based system? And you find in literature quite a few approaches, diagrams where they show you the travel demand, and then they show you areas whether a bus is the most appropriate system, an on-demand service, or a different type of rail-based services. Well, one solution is that we look at different vehicle types. Bus, articulated bus, trams, underground, S-Bahn or commuter trains. They have specific places. The number of places varies with the make. So an underground in Munich may have different capacity than an underground in London, for example. Now here are selected values, just the seats. Yeah. Next time you travel by bus, look and check how many places this bus offers. And it may also differ between urban buses where we have more standing seat possibilities and regional buses where we have more seats. Now, depending on your quality, you have place for standing. And if you want to save money, you put 6 persons per square meters in peak hour. This is not very comfortable. You could say, oh, maybe I just work with 4 or with 2 persons per square meter. Now, depending on that, you get a higher capacity or a lower capacity. I call the one here theoretical capacity, and the other one more practical capacity. Theoretical capacity also indicates that, well, we need to distribute the passengers along the train equally, which is not always possible. Well, and then we can look at headways. And typically a S-Bahn or an underground system, they run every 2 to 2.5 minutes. If you have a really advanced system, they manage a headway of 1.5 minutes. But this the bottleneck is usually the station, because the time the vehicle stands at the station, so you have to minimize the time for boarding and alighting. It's more realistic to have values like this. And, well, we can run buses every minute, but if a bus runs every minute, actually it shouldn't be a bus. It should be more a rail-based system. So a typical short headway for a bus is every 5 minutes. And with those values, you can now determine a capacity. And this is a capacity in one direction. And so this is your theoretical capacity, and this is a typical capacity which you can reach in practice. Now, if you look at those values, 30,000 per hour per lane, you get an idea why we need rail-based transport. Because with cars, with one lane, you can transport not cars, but if you work with a certain occupancy rate, you can transport maybe 2,500, maybe 3,000 persons. So an S-Bahn transports 10 times as many people as a car. So instead of having one lane, one track for railway, you need maybe 8 to 10 tracks for cars. So this is one very impressive reason why we need public transport. Now, well, here, of course, it's a different story, but even a bus, if the demand is high, has a very high capacity. Now, the very moment we do that, it indicates that people are standing. So usually this is not a value we achieve within the course of a day because we want to provide people with seating capacities. Then the value is, of course, somewhat smaller, but still much larger than what you can do with the car. Now, the question is, when do we switch from bus to tram to a heavy rail system like an underground or an S-Bahn? It can also be some light rail system with a higher capacity than a tram. And this is difficult, but you would probably argue that in urban areas, you need something around 10,000 passengers per day that you start thinking of a rail-based system. You have countries or places like Colombia, for example, where you have bus rapid transit, where you have articulated buses. They run similar to a tram system. But if you look at places like Bogota, where they have, I don't know, 5 million, 8 million inhabitants, you notice this system is great that they have it, but it's, in the end, the capacity is not enough for a city of that size. So somewhere around that 10,000, that is a value where you can start thinking of installing a rail-based system. If you go to rural areas where you want to have rail, yesterday we discussed it, well, rail will never be feasible with less than 1,000, and even with 1,000, it will not be feasible. It is feasible if we want it as politicians and we want to subsidize this system because people may prefer rail to bus. So much concerning the type of system, and I'm not sure if there's any mathematical method to determine which system is appropriate. I think this is something we discuss and we decide on a political scale. Next step, which part of the network is suitable for public transport? This is the city of Stuttgart with the entire rail and road network. You may see in black, you see the railway network. Here for the commuter trains, the S-Bahn. You see blue, the underground network, and you see all the other roads. And well, if you examine the roads, whether they are suitable for buses, you will identify that fortunately, only a certain part of this network is suitable. So you need to identify, maybe you just, as I do here, you use the system which is served by buses today, but you may amend it, extend it by additional links, parts of the network which are suitable for a bus. And this is important because it reduces your solution space. And well, you cannot use every road with a bus. You need a certain width. You may have problems with parking cars. So only look at the part of the system which you can actually use. With the stop location, often you have stop locations. Of course, as part of the planning process, you can change them, you can modify them, but this is also something you often already find as input. But it might be an objective to optimize the location of stops. Before we start building line routes and timetables, we need to identify running times. And well, if we want to provide quick travel, then we should not add buffer time. So you measure a required travel time or running time. And then the question is, do we add buffer time or not? If we do not add buffer time, we can travel faster. But if we do not have buffer time, we reduce punctuality because there are always some type of disturbances along the route. At the stop, people, maybe with the S-Bahn, you may take your bike, people with maybe people with a wheelchair enter the vehicle, or maybe a large group of passengers. And that then extends your dwell time. So for that, you need a certain buffer time. So this is something we need to decide on. We need to find a good solution. And if you go out, if you use GPS, if you observe it, what happens to your vehicles, you may observe something like that you have off-peak hours. In peak hours, the running time varies, and then in the evening, it may go down. So you could adopt that by saying, oh, I have a specific running time throughout the course of the day. But this is difficult because we want to provide a regular service. And a regular service means that we have a fixed rhythm headway, the vehicles arriving every 10 or 15 minutes. And that is, of course, influenced by the running time. So this is why operators often do something like that, where they either once or twice or 3 times a day change the running time. And they simplify it. So they accept a certain risk of delay. You decide, you move this up or down, and in that you increase your buffer time. And then at certain times of day, you change maybe the headway, but you change the running time. I'll show you one example. Here you see the display at a stop. This is one line connecting, well, 2 places through the entire city of Stuttgart. So it takes 23 minutes in the morning. And then you see with the start of the peak hour, the travel time goes up from 23 to 30 minutes. It stays with 30 minutes. And in the evening, it goes down again. And well, with these 30 minutes, they provide you a timetable with fixed departure times. All you need to memorize at minute 6, 16, 26, there is a service. But you see, it's different in the morning. So often this change in headway is connected with a change. This change in travel time, or running time, is connected with a change in headway. So here you have a 15-minute headway. You probably need faster time, longer headways. You probably just need half of the vehicles, which you need later here for the 10-minute headway. And likewise in the evening. So this is something you need to get clear. And it really happens that if a bus operator starts with a new line, which was never served before, they do trial runs, test runs with the buses, and they simulate, they measure the travel time they need before they make the final decision. Where should we locate stops? Well, if you want to know where to locate stops, you can ask Anita, because she has written papers on that, and she can provide you with algorithms to do that. In public transport planning.
She will do tomorrow, Markus.
Yeah, you do it tomorrow, exactly. So today you have to live with the channel concept where planners, well, they do it out of experience. But of course, what planners know, like the mathematicians, is that if you have few stops, imagine this is building blocks. And if you have few stops, people need to walk longer. So you have more access time. But the vehicle only needs to stop. The vehicle needs to stop less frequently. If you have more stops, well, then you reduce access and egress time, but all travelers running or traveling on that line, they observe more stops. So the runtime of a line depends on the number of stops. And also the passenger access time depends on the number of stops. Short distances reduce access and egress time, but they increase in vehicle time. You can show in theoretical models that there's an optimum spacing, which depends on how you evaluate walking time compared to driving time or in-vehicle time. If it's equal, you don't mind walking, so 1 minute of walking is the same as 1 minute of in-vehicle time. You get shorter, you get larger spacing, but if people don't like to walk, then you get shorter spacings. So this is the optimization problem behind it. In reality, public transport planners often do it in a different way. They decide where they want to have stops. They look at the maps, they look at densities, but they look at guidelines. And I asked you yesterday, what are maximum distances to the nearest bus stop or the nearest metro stop? And we would say, okay, we typically have those distances between stops, not as access and egress time, but if you transfer that in access and egress time, it would end up with a maximum access time of around 5 minutes, 5 to 8 minutes, and for a metro, 10 to 15 minutes. And what we actually do in planning, if you have a model, once your solution is complete, you have decided on the stop locations. We check the number of inhabitants which are covered by public transport. So you have, I showed you yesterday, the distribution of population, and you intersect a GIS procedure, you intersect with the radius around the stops, and you can distinguish, you can have different catchment areas by transport system, and well, then you identify certain places which are not well served, And if you, well, I should have shown the population density behind it. This is a public park. This is also forest. And you may find certain places, for example, up here, where you see, okay, here we have people which need to walk longer than 300 meters to get to a bus. Yeah, this is university campus. This is where my university is. And you see we have an S-Bahn station and we have bus stations, but we have parts of the campus where you need to walk quite a bit. And immediately what you observe, people working here come by S-Bahn, people working here, they more likely take the car. This is why we put the mechanical engineers up there, because they like cars. So this is how planners approach the problem of stops. Next question, how many lines do we need? Now, if you look at an artificial city, a ring city, you can, well, like a cake, you can cut it into pieces. And the more cake slices you have, the better your coverage. So, of course, this solution reduces access and egress time compared to this solution. And if you have tangential lines, looks like a ring line, but it could be different independent lines serving the outskirts, then again you have a better coverage. Now I'm just looking for, in my next slide, I'm just analyzing this simple type of network, and because the first one is about where on what links can you travel, and the next one is your line network. So not just network coverage, but line density. If this was your network, you can come up with different solutions. You can come up with one line traversing the city and a second line. And maybe this is what we think is natural. But if there's high demand from here to here, why not provide a direct line which runs around the corner and with a second line? And of course, you could do something like that. You're not limited to 2 lines. You can come up with maybe 4 lines. So the more lines you have, the higher line density, the fewer transfers you have. This solution reduces the number of transfers. But at the same time, it increases the line route length, which is usually related to additional cost. Now, whenever I give lectures, I distinguish certain type of public transport lines. And I want to share that with you, and then I will briefly discuss how realistic those typical line routes are. Well, a very common concept is radial lines, and the second common concept is diametric lines. This is what you may have sometimes if you have a city, and this is the rural area, and you connect the outskirts to the inner city. You sometimes have it in railway systems where you have a train station, a dead-end train station, where the vehicles have to turn around. A diametric line is usually more favorable because, well, you don't stop in the city center. The city center, especially if it's buses, space is valuable. You don't want to have a big bus station, at least not for your urban transport, maybe for your regional transport. So, and people want to, the destination is not just in the city center. Maybe the destination is a little bit behind the city center. So with this system, you provide more direct services. Now, diametric lines have disadvantages. One disadvantage is that if your city is very long, you catch up delays. So a bus which is longer than 45 minutes in one direction, 60 minutes, it will catch up delays, and you can only recover, or a good place to recover is the terminal. So if the terminal is far away, it's more difficult to recover. So this is why some cities come up with concepts like this, where they have overlapping diametric lines. This is a good concept because the lines become shorter, and at the same time, you have a denser network in the inner city. And, well, maybe people want to travel from here to here. Very few people, or the demand is usually lower for people who travel through the entire city, especially on buses. Well, then you have tangential lines. We have, in some places, ring lines. And, well, you know, famous ring lines, for example, the Circle Line in London, or in Berlin, you have the S-Bahn ring. Now, if you look at those systems, they are often not, well, they are a ring, but they are, in terms of the public transport service, they are not a real ring road, because they often have a terminal where they start and end, but they run around a circle. So ring lines can be a solution in some cities. For bus lines, well, if you have a ring in your city, also a ring line could be a good idea. And then we have feeder lines. You may have a rail-based system and a bus collecting all the people living in the vicinity of that train stop, but a little bit further away. So this is what we do in teaching. And in teaching, we want to give the people an idea about typical systems. And then you go out and you look at the real world, and this is what you see. And this is my public transport line in Stuttgart. And I wonder, well, this is here the city center. And I wonder, what is that? Is it this radial line coming from the outskirts? Well, it would probably be a diametric line, but here it's doing funny things. And for a computer program, it will be probably terribly hard to reconstruct this type of line. Now here you see a result which comes from the fact that in a place like Stuttgart, the bus has two purposes. The bus has connecting function and at the same time feeder function. The connecting function usually is taken by the underground. The underground, here it's relatively easy to identify that they are all diametric lines. They come from different directions, from up here, from here. So they follow this typology I just showed you. But the buses, then they need to serve the rest. And here there is no metro line, underground line. So this is why they installed a bus. But at the same time, they discovered that some people are also living up here, which either they need to connect to this train station or to this train station. So in the end, we have more or less two feeder lines in two directions, which are connected here. And likewise, here, people want to travel not just to city center, maybe also up here. But here you would observe that very few people from here actually travel up to here. They just developed that line, and for some reason, they decided that they have two branches, and for operational reasons, but maybe also for minimizing transfers, they put those two lines together. But you will never, ever have any person traveling from here to here. So this is then the lines we observe in reality are the results of combining two radial lines in a somewhat random way. I'm not sure if it's random, but well, they tried probably several combinations and figured out that this is the best one, using computer-aided planning, looking at the travel demand and the cost. Now we just looked at line types. I want now to look at types of networks. And again, we have start a very simple network, a radial network. You find this structure in many places, but if you look at it in the pure way, then you will find that such a system is not good, at least not in bigger cities. Because if you have a disturbance here at the central transfer point, your entire system stops working. So it's not sensitive to disturbances. So this is why if you go out to bigger cities, you would often observe that they have 3 or more transfer points in the city center. If you go to Munich, if you go to Zurich, if you go to Berlin, you will find that there's not the one and only. One is often the central station, but then you have something like the marketplace or other important places in your city. So that makes your network more robust. And then a very common concept in the outskirts is branching. Because, well, looking at our cake, we have high density here, but we have lower density, which is different to a cake, in the outskirts. So here, maybe a 10-minute headway is sufficient, and here you may need a 5-minute headway. And you can achieve that by overlapping the lines. And, well, in this way, you have a higher occupancy of your vehicles. It makes your system, well, in a city, you can combine it with systems like this. If you have such a system, and many S-Bahn systems in Europe operate according to this principle, you have problems because two lines merge, and especially if this is rail-based, you need delays of one line and delays of a second line. They may lead to certain conflicts. So the more lines you get together on a central line, the more vulnerable your system gets. Now, I want to talk briefly about why line planning is difficult. Anita will do that with you, but just to give you an idea why things are complicated, what we do, if we just look at this simple example I have here with the 4 branches, we can, assuming we have diametric lines, we can, with this equation, compute the maximum number of lines we can find in that network. Yeah, often as planners, we say, oh, we know where our terminals are. This is where the drivers can take a break. This is where vehicles can turn around. So we have, in this example, 4 terminals. And then if you combine all possible solutions, in this case, you end up with 6 possible lines. That is a reasonable number, but usually we have something like maybe 20 or 30 of those terminals in our city, and the number of potential lines goes up to large numbers. And only for this example with the 4 lines, I can now, and that later on leads us to integer programming, I can select certain lines. Yeah, we call that a line pool. a pool of lines which are possible solutions, and then we select from our pool. And if I go for 2 lines, this is the 3 solutions I can come up with. If I allow 3 lines, you see the combination is large. If I go for 4 lines, there are 15 solutions. I'm not displaying them all here. And it goes down if you have only 5 lines, because 5 lines means out of our 6 lines, we just delete 1. And we have the solutions with the highest number of lines, all lines. And now you see that you need to decide as a planner which of those, in this case, 64 solutions, do you choose? Well, here you can see that if you have the constraint that all stops need to be served, 23 of those are not feasible, but we get a large number of solutions. And in this systematic way, a planner would not look at the problem. They would rather do it step by step, incrementally. Yeah, here you see all 64 solutions, whether you want to have those lines. Well, and then selecting the best combination. If it's just 64, I can compute the indicators important for my evaluation. But if it's more than 64, and well, as it's in the power, it goes up dramatically, you cannot do this computation. Now, which solution is optimal? The cheapest solution, the most attractive solution. If we consider not just cost and service quality, but both, we talked about that yesterday, we get Pareto optimal solutions, or we get solutions which are equally good. And in my little example, I just have, assuming that every line has the same price, I can either go for 2 lines, 3 lines, 4, 5, or 6 lines, and then the prices would rise. And for every solution, I can then decide which combination is the best. And you see that I can have solutions. In my evaluation, I simply looked at the number of transfers, nothing else. I find that depending on the structure of the demand, one of those might be the best. I need demand structure for that, and that would be this solution, and the other solutions would have a higher number of transfers. Now we go back to real world networks. Here you see the network, the S-Bahn network of Munich. And here you see the typical solution for overlapping of line branches. So this is a concept we provide to, it doesn't come from a computer, it's a basic concept we want to follow. So we have the core of the system, and then we branch out. And depending on the demand, you may have 2 lines, and they connect then different places, this one, or you can travel down here. And you can combine the branches in such a way that you minimize the transfers, but often you have other constraints because you have, well, certain slots on your tracks, and sometimes those branches are connected out of operational reasons. So this is one typical solution. Another typical solution which we have in metropolitan areas is that we work with different type of systems. So depending on, well, a city may have a diameter of 10 kilometers, but we have suburbs and a big city, Munich, Stuttgart, other places in the world, they serve an entire area and people commute to the city. And for that reason, if you have a long commute from out here, and you do that with an S-Bahn type system, and you stop everywhere, then it would take rather long time. So this is why several places come up with the idea of express systems. If you go to New York, you will see that they have local trains and they have express trains. The main difference is express trains are not calling at every station. So a system could look like this. You have a train which is calling at every station until it reaches the end of the S-Bahn system. And at the end of the S-Bahn system, you start skipping stops, but you still have selected stops where people can transfer from and to the S-Bahn. And with such a system, you can better compete with the car because, well, here we have high densities, and usually here the speed in the car system is relatively low. But if you go to the rural areas, we have low densities, little congestion, and, well, we want to have reasonable fast rail, and here we catch up. Probably here car is faster, but from here, if you have those direct trains with no stops to the city center, you catch up quite a bit of time, and you are usually faster than the S-Bahn train, significantly faster. So this is also a very common concept if you want to compete with the car in metropolitan areas. And, well, how did we develop the concept? I'm not sure if, of course, planners thought about it, but they ended up with different products. You have an S-Bahn train and you have a regional train. And if you look at certain places, you have regional express and you have regional local train. So over the years, it developed this idea that we want to have different speeds and different stop spacing depending on the type of product we have. Now, once we have the lines, we need to determine the service frequency and the appropriate vehicle. And I put that into one question, one problem, because, well, depending on your vehicle size, that may influence your headway. If we have high frequency, that is very good because high frequency means you can approach the stop and the vehicle will come in short time. So it reduces your origin wait time. And whenever you have transfers, if you have a system like a rail system where you operate a train every hour, you really need to take care of the transfers. If you have an urban system where buses run or undergrounds run every 10 minutes or even more often, you don't need to take care of transfers. The transfer wait time will be small. Now, if you have high frequency, it increases service kilometers. This is why sometimes bus operators prefer larger buses with shorter headways, with longer headways compared to smaller buses with shorter headways. This probably is more expensive than this solution. Yeah, because the highest costs come from the driver, not from the vehicle, especially if we're talking about buses. So you have the discussion about which vehicle size is most appropriate, if this one is cheaper and demand is high enough. Large vehicles reduce frequency and are more cost efficient. Now, if we determine the frequency or the headway, we have two reasons or two ways of determining the headway. The first one is travel demand. This is always a good argument. Avoid overcrowding. So we define the level of saturation we want to achieve, and from that we can compute the minimum service frequency we need. The other thing is the idea of a desired service quality. If you look at public transport at night time, often half the headway would be sufficient. But we need to make sure that the people look at both trips, the trips to their destination and back home. And well, they want to have a certain amount of services. And this is why we often work with a minimum headway, even if it's not required, just looking at travel demand. If you want to determine the number of service runs per hour, which is the frequency, you look at the demand, which needs to be forecasted in some way. You look at the capacity, and you look at a maximum saturation level. And by multiplying the maximum saturation level, maybe something like 0.7, you determine the number of runs per hour. Now, I want to briefly discuss this problem of saturation and occupancy. When we do planning, we like to have a little bit of a buffer because it's very difficult to forecast traffic volumes. First of all, our models are not precise. Second of all, within one line, if you have a line running every 10 minutes and you look at the morning peak, you will still find one or two services which have higher loads because there's a school or there's something else along that line starting at a specific time of day. And we have disturbances. If you have disturbances, this means that either the frequency goes down a little bit, but it also means that people miss connections. And then in the next train, you suddenly have the demand coming from two feeder lines. And that leads to high saturation. You observe that quite often in urban systems the very moment you have the disturbances. So this is why we work with a max saturation. And depending on what you do, in off-peak hours, many operators say, okay, in off-peak hours, we want to provide seats. If you have seats, and we are talking about urban transport, not long-distance transport, it's not that difficult if some of the people unfortunately have to stand because you made some miscalculation or because of disturbances. So you can assume a saturation of 100%. But in peak hours, public transport is a very efficient system because it has varying capacity. During peak hours, we can ask the people to stand. This is not nice for the people, but it's good for the city. So we work with the concept of standing passengers during peak hour. But here we need to be careful. If we want everybody to be able to board, we need to work with the concept of maximum saturation. And one guideline in Germany basically says, keep 1/3 of the capacity for this situation, but only in the case of standing. So let's do that in an example. We have a given demand, and well, this is a line. We are traveling downtown, and assume we have a vehicle capacity, could be like a tram, 45 seats or articulated bus, and 80 standing. Now, if you determine the number of service runs you need, you can first look at this cross-section, 350 passengers. We have a total capacity of 125, but we count only 2/3 of this value. If you do the computation, we end up with 4.3 runs, which means we need 5 runs per hour. Then you may come up with the concept that you say, travelers traveling longer than a given threshold, maybe 15 minutes, maybe 20 minutes, they should get a seat. We don't want anybody to stand longer than 20 minutes. In this case, your critical cross-section is no longer here, but somewhere here, because people then stand for 20 minutes. So in this case, we would say our design volume is 250. Our capacity now is only the seats, but now we work with a maximum saturation of 1. That gives you 5.6 runs, so you need to round it up to 6. So you immediately see that this is linked to costs. The service quality you offer depends on the saturation you want, the maximum saturation you want to provide to your passengers. Now, the next step is that we have done that calculation, and now we are looking at one line only. And now we go back, we look at the entire network. And now you have this type of system here, and you have 3 lines. And our calculation shows us that we need 2 runs here, 3 runs here, and 4 runs here. And well, you can translate that to a 30-minute headway, 20-minute headway, or 15-minute headway. And this is where you need to make a decision. You need to make a decision on a system headway or a system frequency. Yeah, you have many railway systems where this is part of the concept. Der Deutschlandtakt. The Swiss have a 1 hour or even 30-minute headway for their rail system. So you determine a system frequency, and you only allow multiplications of that system frequency. And this is an integer number. So if we do that, example, we decide on a system frequency of minimum of 2 runs per hour. Then n could be 1, 2 runs, or it could be 2, 4 runs, or it could be 6 runs. So in this case, we would say this line is fine, and this line is fine, because it's with the same, it includes our system headway of 30 minutes. But here we need to provide more services, so we upgrade from 3 runs to 4 runs. And that makes it easier for us to look at transfers here, because we have a system with a fixed system headway. So the transfer wait times will always be the same. They will not vary depending on your departure time. And this is something which is nice for the people traveling from here to here, because the timetable will always provide them similar travel times with the same transfer wait times. So this is why planners sit down and they discuss a system headway for their system. And here you just see possible solutions. If you have this frequency or this headway, this is suitable with this amount of, or with this system headways. And you decide for one system headway, and well, then you apply this system headway. Yeah? If you go for a 15-minute system headway or a 10-minute system headway, that rules out certain combinations, because a 20-minute headway will never go together with a system headway of 15 minutes. Now, finally, we can compute, at least for periodic timetables, we can compute the number of vehicles we need. The number of vehicles we need depends on the cycle time and the headway. So we need to determine the cycle time. The cycle time is the run time in one direction multiplied by 2, because we have 2 directions, plus the layover time. If we do that in one example, this is what our timetable could look like. We have 40 minutes running time, then layover time 5 minutes, 40 minutes running time, maybe a driver break here or some other reason, recovery time 15 minutes. That would lead to a cycle time of 100 minutes. Now, with that value, you can compute. We already decided on the headway or the number of services. In our case, we computed 6 services and our cycle time is 100, so we need 10 vehicles. Or just simple, you say 100 minute cycle time, our headway, 6, frequency of 6 is 10 minutes, 100 divided by 10, that gives us 10 vehicles which we need. And we can see those 10 vehicles. The first vehicle departs at 6 o'clock, and then we need 10 vehicles until we can reuse the first vehicle again. So in simple periodic timetables, if we apply or if we allocate the lines only within one line, it's easy to compute the number of vehicles. It's different if we have interlining and if we have irregular services, if you don't have a regular system. The last point I want to make, because it's linked to line planning, is the timetable planning. At the moment, we just look at the frequencies. Up to here, set frequency settings and maybe finding lines. Planners, well, depending on the complexity of the system, planners probably perform quite well, but that stops immediately if it comes to transfers. To make transfers is hard work if you have a given network. Yeah, you see we have this, here we have this triangle, and now try to find optimal departure times here at the beginning that you minimize transfers. That is something which is much better to do with a computer. What do we want to have if we have a terminal stop where lines have to turn around? We want the lines to come in, the lines to go out, and all lines meet here and all lines go out after maybe 5 or 10 minutes. If you have a hierarchy in the system, this could be the intercity train, this could be the regional train. You have a different system, you want to minimize the stop time for the intercity train. So this is what the system could look like. And it doesn't look that different if your central pulsing node is at an intersection node. This is what you want to achieve. Now, you can achieve that either by running optimization algorithms, optimizing your timetable, or you can do it the way, for example, the Swiss do it. You can do it not just by timetable planning, but also by network planning. This is the Swiss system in the year 2004, where they had, they had running times of 30 minutes between quite a few of their main cities. And here they had 60 minutes. But they had places where, well, the travel time didn't really fit with the idea of a timed transfer system. So the Swiss optimized their timetable by, over the years, not investing necessarily in high-speed rail, but if you look it up here, they made changes to the system. Those 75 minutes, they were now, by, I don't know what they did, building new railway tracks, they were reduced to 60 minutes, and then they are within the system. So you see that they prepared their entire system for a 60 and a 30-minute system headway by investing in the infrastructure. So instead of, before you actually start your optimization, your timetable optimization, you try to provide a good background system, good constraints for your algorithm by determining those timed transfer nodes and by working on the running time between the stations. Now, this is a different concept where you see that optimization sometimes is not enough because you need to optimize not just the timetable, but the entire network. And if you have such a system, then timetabling, it's not easy, but it's easier compared to a system where you didn't look at the link travel times. So this is what I wanted to tell you, but I want to conclude with an example. It's an artificial example, and I hope it helps you to understand how planners may think when they develop a network. Imagine we have a very simplified network here. Given is the railway system. And here we have rural roads, and we want to determine the bus network for this system. So you have some places, A, B, C, D, E. We have the running times between the places. And we have the demand. And well, if you look at the demand and the demand matrix, you notice it's hard to get to understand those OD pairs. So we first do an assignment. We do an assignment. We call that this assignment of desired lines. So assuming people take a taxi. So that would provide us for the morning peak. You see that we have certain volumes. Now, the next thing is, you know the capacity of your bus, and you divide the volumes, the 170 by 50, and you round it up, and you see that you need 4 services, a frequency of 4. And here you see a frequency of 2. And then if you look at it, you see that this is slightly different. You have more demand on this axis than on this axis. And if we know that this system also has a frequency of 4, well, then as a planner, you probably immediately see that, okay, this is my system headway. I will go for 4. And here you need to think maybe 2 is enough. But then the question is, where should we stop? Where should we break 2 bus lines? Now, the next thing, especially in rural areas, what you do, you think of a suitable system headway. So as the S-Bahn runs every 15 minutes, those are suitable headways. We just talked about that. So next step, I now look at this station, and the train system, the S-Bahn system, is the system which defines arrivals and departures. So here you have this this is traveling towards station X. So they arrive at minute 5 and minute 10, and then they travel back. So you as planner then think of potential departure times of your bus. And once there are several solutions, you can do it in a different way, but one possible solution is that you adapt to the train system and you arrive at the same minute, then people have 5 minutes of transfer time. And likewise, coming back at minute 5 minutes, and they travel out into the countryside. This would be the second step. So we already have our skeleton of our timetable. And then I already go back to possible vehicle schedules. I'm looking at cycles. And well, we start maybe here as one solution, but it could also be here. Then we would start earlier. We travel to the station. The vehicle turns around and travels back. Here you could argue, oh, maybe I can travel back straight away. Maybe I want to schedule a driver break or a recovery break. What you could actually do, I'm not doing that in my example, but in practice you would probably do that. You would run here with very short layover time, because we are in rural areas. You're traveling not in the direction towards the city, but out of the city. So usually you will have little delays, so you will be on time. You could serve this service directly back, and then this one, and only around 9 o'clock, when we probably go back to a different headway, then you schedule your first driver break. But this is something you can then decide later on in vehicle scheduling. But for my basic vehicle schedule, I assume this pattern. And if I assume this pattern, I then can think of suitable service times. Here you see my pattern. I have service time, layover time, service time, layover time. So I can write an equation which says my cycle time is the service time multiplied by 2 plus my fixed time for the layover, 15 minutes and 5 minutes. And now I can test possible cycle times. And I have my system headway of 15 minutes. So I can work with 1, 2, 4, 6, and 8. And if I do that, imagine I select a cycle time of 30 minutes. Then I have 20 minutes as layover time, and only my entire cycle is 30 minutes, so that only leaves me with 10 minutes of service time, and I have 2 directions. So that would be a pretty stupid cycle, because I would travel for 5 minutes, then the driver has a break of 15 minutes, and then traveling again for 5 minutes. So maybe the drivers would like that, but you mainly pay for the breaks. And what I'm doing here is I'm changing the cycle time, and you see, depending on the cycle time, of course, I get more service time per direction. And then I look, what is the service time I actually need? For this example, I need, in one direction, I need 20 minutes. So I need this type of cycle to serve this OD pair A to X. And for this one, a cycle time of 60 can be combined with a headway of 15 minutes, a headway of 30 minutes, and a headway of 60 minutes. So I have these possible solutions for lengths of lines. My line can be either 20 minutes long, or 35 minutes long, or 50 minutes long. If my line was only 45 minutes long, I would lose a certain amount of service time I could spend. And this is what you then use for planning because maybe you take a little detour because you know, oh, you have some reserve and you could serve a little bit more of your area. Well, and with that, you can now come up. A planner wouldn't do it like that, but just to show you the solution space, you could check and say, I want to stop bus line 1 here and bus line 2 here. So my breakpoint is A. That is this solution. I have a bus ADX, this one being complemented by a second bus serving this line route. Or a second solution where my breakpoint, my terminal is here, and I likewise did it for this location. Or you could have a circle line serving this entire area. And for each of those, you can now determine the service time in one direction, 20 minutes. This one requires 30 minutes. If you do it the opposite way around, 10 plus 10 plus 18 plus 10 gives 48 minutes. So this is what the service time we need. And now I can go back to my previous calculation and I can compute the required cycle time. And I need to round it up to suitable cycle times. Yeah, here you see I lose 4 minutes, which I'm of additional standing time. And I can always then determine where the vehicle stands. And you see here, it's the standing time, and the standing time goes up. Well, I have the 15 minutes scheduled standing time, and those 4 minutes are additional standing time, which are not productive. So depending where I end, where I locate my terminal, I have more unproductive times. Looking at my timetable, my cycle time here, and a headway, I can compute the number of vehicles. So if I have a cycle time of 60 minutes and a headway of 15 minutes, I get 4 vehicles. If I have a cycle time of 30 and a 30-minute headway, sorry, a cycle time of 60 and 30-minute headway, I need 2 vehicles, and so on. So for any combination of headways, I can compute the number of vehicles I need. And well, if I then sum it up for each solution, I find that for this line, a 30-minute headway is enough. This is what I computed earlier with looking at the volumes. So I have a 15-minute headway on that line and a 30-minute headway on this line. And in total, I would need 8 vehicles. And if you look at the other solutions, you would find that you need more vehicles. So in that case, the solution where you have your terminal here is the best. And then you can come up and produce your schedules. So this is the schedule of the first bus. Here is this A place traveling to the station. And this is the second bus. I'm taking the longer route. And here you see the vehicle schedules. Every color is one vehicle schedule. And then you know the number of vehicles you need, and you do your final assignment, and you are finally done with your integrated transport planning, where you look at travel times and at costs at the same time. This is a manual process where you see where we created the timetable, we constructed a timetable. And of course, this is, well, a simple case because it assumes that we have this time of transfer point. It's quickly getting more difficult if you have more than one transfer point. But since many of our networks have this hierarchical structure where you have the train system and then the feeder bus system, this idea works. But imagine you have a second S-Bahn line here. Immediately you want to have computer-aided system because it's more difficult to find a good solution for that. So that was the input I wanted to give you, and I made it perfectly in time. Thank you for listening, and now we have time for a break, but we also have time for asking questions.